Question 11, we have Boltzmann distribution. So it simply tells you how the energy is spread amongst the molecules. So no molecules have zero energy because your temperature is greater than 0 Kelvin. You have a certain amount of molecules that have overcome this much activation energy. So activation energy is on the x-axis. It's just a value allocated at these high energy regions, minimum amount of energy that reacting particle must have before they can undergo a reaction there. So which statement correctly describe the changes if the temperature is increased? So what you do in this kind of question is you try and draw what happens when temperature is increased. The whole graph will shift to the right. What you get is this is the peak. The peak will be lower. The peak will be lower. As you can see, there are lesser number of molecules with this most probable energy. So this is most probable energy. Now the most probable energy would have changed compared to what we have previously at the lower temperature. So this is the most probable energy. This is lower temperature. What we could see is at higher temperature, there are two changes to the Boltzmann distribution. The whole thing goes down, but at the same time you also get greater proportion of effective collisions, not just these blue shaded regions, but you also have these red color shaded regions on top of the blue color region, because everything under the graph, there's the number of molecules out of the whole number of molecules that have enough energy greater than or equal to EA to react. So at a higher temperature, so this is higher temperature, as temperature is increased, fewer molecules. Let's go to something else which you can understand easily. The area under the graph increases. Nope, they stay the same because this is under the curve. They don't say above or greater than EA. It just say the whole thing. That means the area under the graph, the total area under the graph represent the total number of molecules. Just by changing temperature, you do not change the number of reactive molecules. So D is wrong there. Now part C, option C, more molecules possess the most probable energy. We get lesser molecule possess the most probable energy. So more is wrong. It should be lesser molecules possess the most probable energy. And this value shift to the left, that is wrong. It shift to the right at higher temperature. Now between A and B, so fewer molecules possess the most probable energy. Fewer there means lesser, so indeed it is lesser number of molecules possess the most probable energy. And this value has shifted to the right hand side as you have gone from that lower temperature, most probable energy, to the most probable energy at the higher temperature. So it shifts to the right, and you have fewer molecules that possess the most probable energy. Question 12, this is about group 2 metal nitrate, and this is anhydrous, so this is not hydrated. We don't have to worry about water vapor being produced as one of the product here because you're not losing the mass from the water of crystallization or whatnot. So group 2 nitrate, M2 plus, NO3 minus, so MNO3 twice. When you decompose that, you're going to get group 2 oxide, M2 plus, O2 minus. You're going to get NO2 gas, a brown color gas. You're going to get oxygen gas, 6 oxygen atoms, 1 and then 4 oxygen atoms. You only need 1 oxygen atoms there. So what you get really is you get half oxygen gas molecule there, 2 moles of NO2, 1 mole of group 2 oxide coming from 1 mole of group 2 nitrate. Some students or some teachers, they really like to have a whole number only, so they'll multiply the whole thing by 2. You get 2, 2, 4 and 1 there. Doesn't matter. When we decompose these, we produce this much gas. So this gas really is NO2 and O2. So you cannot really just attribute or allocate this just for the NO2 or for the O2. In fact, all of these is 1.53 gram. We know about reacting masses. Whatever goes in is whatever comes out. You put 3 gram in, you lost this much. Therefore, the mass of the group 2 oxide form must be the difference. This is called the idea of conservation of masses. Mass is not created nor destroyed. They get converted from one form to another as it undergoes a chemical reaction here. So what we have there really is we need to work out the MR. So the MR of the group 2 nitrate, so you have M, which we don't know what M is, and we can work out from the M the identity of the metal with the periodic table later on. I've got 2 of the nitrate, so I got 14.0 plus 16.0 times 3, I get 62.0. So put that onto the calculator, 62.0 times 2, I get 124.0. I'm just going to do 124 to make my life easy. So this one is M plus 16.0, M plus 16, 1 oxygen there. I'm ready to see that this is 1 mole is to 1 mole, so I can clearly see that the mole of the group 2 nitrate is equal to the mole of the group 2 oxide. So the mass of the group 2 oxide is 1.47 divided by M plus 16, and then this on the left hand side you have the MR of the group 2 nitrate. We have the mass of the group 2 nitrate 3.00 gram like that. Now, I'm gonna move up and then do some expansion. Okay, so 3 times M plus 16, so that is 3 times M, 3 times 16, and there's 1.47 M plus 124. There's 1.47 times M and 1.47 times 124 there. Hopefully you can see the mathematics fairly easily. So there's 1.47 M, and then in my calculator for the next one, 1.47 times 124. This one is 182.28. I'm going to move the M to one side, so collecting the terms that have M together, you are just doing some simple mathematics. 3 minus 1.47. These give me 1.53 M, and then 182.28 minus 48. 182.28 minus 48. I get 134.28. Last but not least, you're going to divide them. So 134.28 divided by 1.53. Running out of space here, so I'm just going to write on the other side. So divided by 1.53. So they give me 87.8. So from your predict table, you're going to go to something that has, this is actually the MR of the group 2 metal. So have a look at your predict table. So look for group 2 metal, something that have MR of 88, that is going to be strontium. So therefore, M equal to strontium in group 2. So our nitrate is going to be strontium nitrate there. Question 13, what happens when a piece of magnesium is placed in cold water? We know that magnesium reacts very, very slowly, almost no reaction with cold water, but magnesium can react with steam, okay? So only with steam. And it will get not magnesium hydroxide, but instead you get magnesium oxide and also hydrogen gas when you react it with steam there. So a vigorous effervescence is wrong. That is typical for group 1 metal. Bubbles of gas form slowly is kind of correct. The magnesium floats on surface, that is wrong. So only the lithium, sodium and potassium have lesser density than water. So that is part of your group 1 case study from O-level, GCSE as well as IGCSE level chemistry. But here reacts quickly should already told you that this one is wrong. It's not a rapid, it's not a vigorous reaction. Now the magnesium glows and the white solid is produced. This one is wrong. This one is combustion of magnesium. That one is magnesium burns in oxygen, not reacting with cold water. So be very careful about your observation there. So B is the only correct answer. Question 14. Compound X releases carbon dioxide and you get a white solid when it's heated. So you get carbon dioxide and a white solid when it's heated. The oxide itself is not going to release carbon dioxide because the oxide itself, they're looking for X. So where you're going to get the carbon dioxide, you get it from carbonate decomposition. If you have only the oxide, you are not going to release carbon dioxide. From where are you going to get the carbon? Therefore, we're just looking at option A and option C here. But neither X nor Y are soluble in water. So we know that when this decomposes, it's going to give you calcium oxide and CO2. And then this will give you MgO and CO2. So neither of the products, neither the carbonate nor the oxides are soluble. So that's what they're saying. This is the metal oxide. This is the group 2 metal oxide, whereas X is the group 2 carbonate, metal carbonate. Compound Y is used as a refractory kiln lining. So this is a use of MgO. So compound X really has got to be your MgCO3 there. Okay, so we know that solubility of the group 2 oxides, so this one will give you pH 9, not very soluble at all. Okay, calcium oxide is slightly soluble in water. You're going to get a saturated solution of calcium hydroxide, which is actually what you call lime water. Use it to test for carbon dioxide. Okay. Question 15. So we have a funny graph here. This is electronegativity against first ionization energy. So in terms of the electronegativity of the elements, sodium, magnesium, aluminum, silicon, we know that across a period, the electronegativity will increase. Fluorine being the most electronegative, which means everything to the left of fluorine electronegativity decrease that way, but we're going from left to right, so electronegativity will increase that way. So therefore, we're looking at silicon having the highest electronegativity, sodium having the lowest electronegativity. I'll check my y-axis first. Silicon have the highest electronegativity, sodium have the lowest. Sodium have the lowest electronegativity, silicon have the highest electronegativity. Sodium has the highest electronegativity, C is out. Sodium has the highest electronegativity, D is out. Okay, now left between A and B, I'm left to check for the first ionization energy. Seems like sodium and silicon, their first ionization energy is fixed. I really just need to check for aluminium and magnesium for my first ionization energy. We know that as we go from magnesium to aluminium, we are filling in the p subshell. So starting from the neon configuration, I get 3s2 there. But I will fill the 3p orbitals. When you think about the 3p orbitals, we have the s, which is a spherical orbital, and then the p orbital, which is dumbbell shape. When your electrons are in the p orbitals, they are further away from the nucleus. So they are further away in the p orbital. Further away from the nucleus when you are in the p orbitals, and therefore more shielded, and therefore slightly easier to remove as you don't require that much energy. That is why from magnesium to aluminium, there is a drop. That is your first drop in first ionization energy. So in terms of ionization energy, aluminium will have a lower first ionization energy than magnesium. Here magnesium has a lower than aluminium, which is actually wrong. It should be the aluminium that has lower first ionization energy than magnesium. Am I correct? What does this graph looks a bit funny? This graph does look a bit funny. In terms of first ionization energy, so I know first ionization energy, this is definitely wrong, but I'm just concerned about the electronegativity as well. What exactly is wrong? Well, I guess perhaps the electronegativity is indeed kind of strange there. But we know from first ionization energy, we know that first ionization energy definitely there is a small drop, increase, decrease, increase, decrease, increase, and then decrease all the way. We know that that is a result of filling in group 1, and then group 2, group 13, group 15, group 16, the second drop due to paired electron repulsion. And when you fill a new shell, it's going to go down there. So magnesium is there. Aluminium will have a lower first ionization energy than magnesium. Here, aluminium has a higher first ionization energy than magnesium. Aluminium has a higher one than magnesium. This could be correct. However, in terms of electronegativity, silicon will have a higher electronegativity than sodium. So I can't do anything. B turns out to be, B must be the correct answer despite the electronegativity trend. Actually, that's fine because sodium followed by magnesium followed by aluminium. I don't know what I was talking about. I thought I made a mistake there. But this kind of graph can be, not a graph, this kind of diagram could be difficult to read, right? Sodium increases in electronegativity to magnesium, to aluminium, and then to silicon there. Hopefully that makes sense to you, how I actually break the question down. Question 16 is about electrolysis of brine. This is a saturated or a concentrated aqueous sodium chloride. And you know from your O-level, GCSE or IGCSE level chemistry, something you have learned from before, you get H plus or H minus like that. But when you have concentrated solution, you're going to favor the Cl minus. And then between the cations, you're going to still favor the H plus there. So what happened there is that you're going to get the Cl2 at the anode. Of course, I am not writing the balance equation. You're going to get a reduction at the cathode, and then you're going to get oxidation at the anode, where you have loss of electrons and you have gain of electrons at the cathode there. Leaving behind, what you left behind is this Na plus OH minus, and you're going to get an alkaline solution. Now, solution of sodium chloride 1, that is ClO minus Na plus. You can work out the oxidation number. NaClO, common product in disproportionation reactions when you have NaOH reacting with Cl2, classic group 7 disproportionations. You're going to get NaCl, you're going to get NaClO, you're also going to get H2O. This is chlorine minus 1, this is chlorine plus 1. Because the sodium is plus 1, the chlorine is plus 1, the oxygen is minus 2, the overall compound has no charge whatsoever. Balancing the equations, so I get, yeah, there's balance already. Okay, so this is chlorine 0. Now this is called disproportionation because it's a special type of redox where one species is both reduced and oxidized in the same reaction. So we are mixing the NaOH, as well as Cl2. Now this is CO2. CO2 is produced at the anode, so really we're looking at the anode, and we're looking at the product P. So P must be the CO2 and not Q, because Q is H2 at the cathode and this is CO2 at the anode. Now between R and S, so what happened is it's only after the reactions that it passed through the diaphragm. So what are we going to get here? So you don't really have the H plus, and the OH minus, they're still lying around in here. It's only when they pass through the diaphragm, the remaining 3 ions, except the Cl minus, which get discharged. So the H plus, OH minus, and Na plus are going to lie in here, but the H plus get discharged, and only then you're going to get S, which will be the Na plus and the OH minus that get left behind. So it's actually the S, which contains the sodium hydroxide, and therefore that is P and S. There's option B there. Question 17, which statement about the ammonium ion is correct? Just like one of the earlier questions, it was pH3 plus H plus. You get this when you have NH3 and H plus. So what we get is we have a lone pair on the nitrogen, and that one can donate both the electrons to form these covalent bonds. It's a very special covalent bond. They call this dative covalent bond because both the electrons in the covalent bond come from only one atom. When you do this, the nitrogen in the ammonia, which I haven't shown you three-dimensional structure here, but very clearly going from the left to the right-hand side, there is a change in geometry. So when that add with H plus, there is a change in geometry because here you have 3 bond pair and 1 lone pair still available on the nitrogen, but here you got 4 bond pair and 0 lone pair. So what happened with the presence of 1 lone pair, that will repel more than the bond pair, whereas when you only have no lone pair, the 4 bond pair will repel equally. And as such, this is going to be trigonal pyramidal 107 degree, and there's going to be 109.5 degree. There's actually tetrahedral. I have not drawn to show the shape. If you want to show the shape, you have to draw 3-dimensional diagram and not this lousy diagram, which is just display here, which doesn't show you the geometry at all. So all the bond angles are 107. That is wrong because we're looking at ammonium. It's tetrahedral 109.5 degree already. And ammonium ions are formed when ammonia behaves as an acid. Nope, it will accept protons. So the NH3 accepts the H plus, and when you accept the H plus, that is it acting as a base proton acceptor there. So acid is wrong there. Ammonium ions are unreactive when you hit it with NaOH. That is also wrong because we know the test for ammonium ions is when you hit it with OH minus, then the NH4 plus acts as an acid, it donates the protons, the OH minus acts as a base, it accepts the protons, you're going to get neutralization, H2O and NH3. They don't call this neutralization because you are producing ammonia which is alkaline, so instead what they call this is a displacement reaction. But in reality, this NH4 plus is acting as an acid, donates the protons, the OH minus is acting as a base and accepts the H plus in forming the water, leaving you behind the NH3, which comes back and which you recover as a base there. The bonds are all the same length because of hybridization with 4 bond pair and 0 lone pair. 4 plus 0 give you 4 electron pairs. This is actually nitrogen sp3 hybridizations. 1 plus 3 give you 4 electron pairs. With hybridizations, you can be assured that all the bonds are of the same length, all the bonds are of the same energy. Question 18, we have a couple of these pollutants. So which reaction concerning these carbon monoxide, nitrogen dioxide, and sulfur dioxide occurs in the atmosphere? The CO is spontaneously oxidized to CO2. Okay, so let's write some equations. The word there is spontaneous, and then the NO2 is reduced to NO by using CO, and then what could we get? We get CO2 like that. Is it? Okay, so the CO steals away the oxygen and becomes CO2. And what about option C here? The NO2 is reduced to NO by SO2. So the SO2 steals the oxygen and you get NO. And then the SO2 is oxidized to SO3 by CO2. You're thinking about similar to this reaction here, but instead of NO2, you get SO2 going to SO3 with the help of CO2. Now I can tell you that option D is absolute bollocks because this is our key equation. C is the correct one. But I'm just thinking about the rest of these. We know that this is not spontaneous. This happens in your catalytic converter. You think about catalytic converter, you have heterogeneous catalysis where you need to have rhodium, palladium, platinum, iridium, precious metals in your catalytic converter, rhodium, iridium, blah 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 as your catalyst, heterogeneous catalyst, as these are gaseous phase reactants, and you have transition metal solid as your heterogeneous catalyst. So spontaneous is actually wrong. They don't spontaneously happen in the atmosphere. D is wrong. Now between B and C, we know that it's not the CO2 that is our reducing agent. It's not this reaction that happened. It is definitely option C, which is to do with the environmental chemistry. Okay. We also know that continuation to this, that the NO2 is acting as a catalyst because the NO can react further with the oxygen to give you NO2. And then in terms of the three equations that you typically have to associate with the formation of acid rains, now that we get the SO3, not from contact process, but from this natural oxidation of SO2 to SO3 with this oxide of nitrogen in the upper atmosphere, the SO3 can then dissolve in rainwater, and SO3 plus the H2O, this is sulfur plus 6. You're going to get the sulfuric acid, where this is sulfur plus 6 as well. This is your acid rain formation, okay, all the way from SO2 with the use of NO2 as a catalyst. That is why you get NO2 regenerated, because a catalyst is not used up in the reaction. It simply speeds up the rate of reaction. Now question number 19 is about redox equations, and we have this between chlorine and this hot aqueous sodium hydroxide. So this is the more extreme disproportionation, where you will not stop at chlorine plus 1. Instead, what you have is it will stop at chlorine plus 5. It's told that it's chloride 5. If you think about ClO3 minus, minus 1 is the oxidation number of the ion because the charge of the ion. You have 1 chlorine, you have 3 oxygen, each of which is minus 2. So the chlorine is going to be minus 1 plus 6. Chlorine is plus 5. It's called chloride 5 ions. What we have here is we have changes in oxidation number. We can use changes in oxidation number to balance redox equations. This is as stated in the redox topic. Use changes in oxidation number to balance chemical equations. 0 to minus 1 is a decrease of 1. So there's minus 1 there. And then 0 all the way to plus 5 is an increase of 5 oxidation number there. In terms of redox, we're going to multiply these so that the changes in oxidation number are equal and balanced. This multiplied by 1, this one multiplied by 5, so that I'm going to have just 1 of these and 5 of these. If I have x equal to 5, then it's going to be that, and y is 1. And having said that, then 5 chloride, well 5 chlorine if you count just the chlorine atoms, and 1 chlorine, that's going to give you 6 chlorine atoms. But I have a chlorine molecule, that is why I have 3 in front then, because 3 times 2 give me 6 chlorine atoms. The equation can be balanced further if you think about the number of hydrogen and number of oxygen here. So 3 oxygen, and what do you have? What's the next best thing to do? It's actually easier if you have the Na plus and Na plus, because if you have NaOH, 5 Na plus 1 Na plus, therefore you will need 6 Na plus, so you will need 6 NaOH. Having said that, 6 oxygen, 3 oxygen, you just need 3 more water, therefore 6 H plus, 6 hydrogen there, okay? Question 20, which alcohol will react with acidified solution of potassium dichromate 6? By right, this has to be acidified. Without the acid, it will not work as a redox reagent, as a oxidizing agent. You know it in the theory paper that if you don't write something like this, you don't get the full mark because you will be missing out on the acidified conditions. This also have to be reflux there. Now we want to get ketone. So ketone is oxidized from secondary alcohol, and that will give you a ketone. And you want 6 carbon atom. The first thing you do is draw out what these names represent. Butane 1-ol, so there are 4 alcohol. I always like to draw skeletal formula. It's the most elegant, it's the fastest of all. I have OH at position 1, 2, 3, and 4. There are 4 carbons, OH at position 1. I have 2 times CH3, it's called dimethyl, so 2 times CH3, both of them is at position 2, so 1 and 2. Methyl and methyl, dimethyl, 2 dimethyl there, okay? This very clearly is a primary alcohol because the carbon with the OH, the carbon with the OH is bonded to one other carbon. Primary alcohol does not oxidize to give you ketones, instead give you aldehyde and potentially could give you carboxylic acid if you reflux it. You get aldehyde if you heat and distill immediately. So A is definitely out there. So next one, pentantriol. So draw 5 carbons, 1, 2, 3, 4, 5. I have an OH, pentantriol. The OH is at position 3. I have a 2-methyl. That thing is there. And then what I get is the carbon with the OH is bonded to 1 and 2 other carbons. This is a secondary alcohol. However, when you oxidize this, you are still going to get a ketone, and that is 5 carbons in the main chain. However, you do have 6 carbon altogether because you have this side chain there, side branch. So altogether, total of 6 carbons, and it's a ketone. So meaning to say B must be our answer there. Okay, I thought B wasn't going to be the answer when I saw the 5 carbons, but I forgot to count this side chain there, which is actually there. So 5 plus 1 is 6 carbons. Let's just go through the other option. So pentan 2-ol, 1, 2, 3, 4, 5. You got an OH there. You got a 3 dimethyl there. I don't need to count. I can see there are 5 carbons, and then 6 carbon is 7 carbons. So 7 carbon total. When I do oxidation, I'm going to get 7 carbon total again. So that doesn't give me the answer at all, which because I want 6 carbon atoms in the ketone. In terms of D, so I have pentan 3-ol. So this is pentan 3-ol. But I've got a 3-methyl, so I introduce another CH3 there. Now the carbon with the OH is this carbon number 3. This carbon with the OH is bonded to 1, 2, and 3 other carbons. This is what we call tertiary alcohol. Carbon from 4 bonds, 1, 2, 3, and 4. There are no more hydrogen on these carbons with the OH, and therefore no more hydrogen to be lost means you cannot do any oxidation at all, because oxidation involves the loss of hydrogen in the context of organic chemistry. So no hydrogen on the carbons with the OH, tertiary alcohol cannot be oxidized. No oxidation at all. Your potassium dichromate 6 acidified will remain orange. All of these A, B, and C will give you orange to green coloration because that is your chromium plus 6 in the dichromate, going to chromium plus 3 in your chromium 3 plus aqueous ion. And what this color change represent is this is orange in color, and this will go to green coloration, whereas for this tertiary alcohol, it will just remain orange because no oxidation will be observed for tertiary alcohol.